here was motivational. So after this motivational interaction, why it is interesting to study statistical field theory, and why the concept of field is relevant, especially when there are length scales that diverge, like in second order phase transition at the critical temperature. Let's now forget for a moment all this motivation and start doing some stuff, some real field theory. So for us, a statistical field theory will be nothing less than a system with a canonical partition function, which is an object that I can use to calculate averages and equilibrium of observables. And this partition function is not a function of the position of the particles, but is a function of a stochastic variable defined in each point of space that we call the field. So if we discretize, this will be integral over d1, dphi2, and so on and so forth. So if I have a point in each point, if I have a mesh, I can define phi1 here, phi2 here, and I order phi3 and so on. Or I can say, perhaps better, I integrate over a value of the field and I distinguish, I label them by their position. X, say, for instance, I can say IA plus BJ plus C. Oh, sorry, let me write it this way. And XIA, or I can leave it A, right? Okay, and X and Y and Z, right? When NX and Y and Z are integer numbers with respect to an origin, which point to a particular point of space, where I have made, say, NX steps in the X direction and Y steps in the Z direction, in the Y direction, and Z steps in the Z direction, right? And I integrate over all NX and Y and NZ. So I'm integrating over the values of the field in each point of space. So, and this partition function contains a Hamiltonian that depends on all these values of the fields. I'm going to write it in Word, and then I use a better notation in a moment. So it contains an Hamiltonian, and the Hamiltonian depends on the values of the field everywhere. So what am I saying here? I'm saying that my dynamical variables are fields in all points of space or in a lattice. So for each of these points, I have a corresponding variable that I need to integrate, d phi. Okay. So when I make the continuum limit, I have an infinite number of integrals in the partition function because the number of lattice points I have becomes infinite and continuous, right? And in each point I have a variable to interact, to integrate. So this is exactly a functional integral, right? Because what am I actually doing? I'm integrating over all possible values of the function phi. To visualize this, let's do in 2 dimensions. Let's suppose I have a grid here. So I have all these possible points where I define the fields. And of course, on the y-axis, I define the corresponding value of the field. So for instance, this point is here, this point is here, this point is here, this point is here, this point. So if I were to draw it, I basically have a sheet. If this is a continuous smooth value, for instance, I would have my field would be defined over the entire space, and it's a function defined on space, right? Okay. So to integrate over all possible values of this field, it's basically a functional integral. And the Hamiltonian will depend, of course, on the value of the field everywhere. So I will denote it as a functional of the field. And the exponent here is in squarely bracket, not in curly bracket, not in square bracket, because it's not a functional. So this is a functional integral. And this is, of course, a functional. Okay? So this is a field theory. Nothing more, nothing less. So we want to understand field theories. We want to use field theory to compute equilibrium properties. That's the goal of statistical field theory, if you want. So in order to do that, let me introduce, well, let me consider one specific system that we shall use as a prototype for much of our discussion. So rather than being completely general, in the next couple of lectures, we'll be sticking to one particular choice of the Hamiltonian. And so we're going to make some assumptions that are coming from this intuitive intuition that the notion of field is very useful near critical points, because near critical points, correlation lengths diverge. And therefore, if the correlation lengths diverge, my fields on average, which describe correlations, my fields on average will vary very slowly. The average of my fields will vary very slowly, right? So I will, in addition, near critical points, the numerical value of this average will be very small, very close to zero. Because remember, for instance, in the magnetization case, we are interested in here, and the field near magnetization, the average value of the field is very small. So the idea is that out of all possible Hamiltonian, I can imagine, I don't know the Hamiltonian function, but I can use effective field theory arguments to build it. Remember the first lectures? I can say, first of all, I can tailor expand this and build this as a sum of terms involving at most the most general term containing powers of the fields and their derivatives, right? Now, the higher the number of power, the higher the number of power of fields, the smaller the contribution to the Hamiltonian will be, because we are near the phase transition where fields, the very average fields, the very average value of the fields are very small. So phi to the fourth is going to be smaller than phi to the second on average, because phi is small on average. Okay. In addition, Large derivatives will be small quantities because the fields changes very slowly, since the typical length scales over which average values of fields change is the correlation length, which is defined to be an infrared scale. Okay? So higher derivative of fields will play lesser role than low number of derivatives of fields. Okay? And finally, I want to write a Hamiltonian that is compatible with the symmetries of my system. Now, if you think this way, then it clearly comes off in that, of course, you will have a term like, well, you will have a term constant with no fields, but that's just a constant and you don't care. You cannot have a term with just one field unless you have a magnetic field, because that will break the invariance of the system by reflection over the z-axis, right? So I cannot have a term C1 phi unless I have a magnetic field that breaks the symmetry. Okay? We will put it there later on, but let's forget about it for a moment. Okay, let's use the effective field theory arguments to build a reasonable Hamiltonian. So I'm going to have a term like second order term. Let me call it R naught phi square of x. That's a legitimate term because it is invariant under reflection. Phi goes into minus phi. And it's a low power of fields. Of course, I can also have a terms u naught over 4. Let me put a 4 factorial here for a reason that will become clear later, but you can also not put it and rescale u naught. And put the fourth power here. Why not? But I know that the fourth power, I expected that under, the sixth power will be smaller than the fourth power and so on and so forth in general. Okay? But like I said, we can also allow derivatives. I cannot allow a term like C3 phi to the q because it's not symmetric under invariant under inversion of the z-axis. So also this is ruled out. The next term I have is the one involving derivatives. For instance, a term like this with its own context. Okay? This is a nice term because it has low number of fields and lowest possible number of derivatives. I cannot just put one derivative because I cannot make a scalar with a single derivative. But I can neglect any higher order of derivatives, for instance, this term, because derivatives are small quantities because the fields changes very slowly. So to say, the simplest theory I can imagine is one that contains one derivative terms and up to fourth order polynomial. Of course, the simplest one would be just this. The next two simplest will be this, but these two theories happen to be trivial, as we shall see. And we will solve them exactly analytically, but they're very boring. So let's put at least this term in to make it a little bit spicy. Okay, so in the end, what we have obtained is the famous super celebrated Landau Hamiltonian derived from the language of statistical field theory, of effective field theory, right? Normalization group-based idea of putting the most general Hamiltonian compatible with the symmetries and neglecting higher order effects. Okay, and what is the theory? The theory looks like the following. Now, as you can see, I have not put my constant into this term because I can always reabsorb one constant into the definition of the field. And say if there was a constant, say C bar here, I can call C phi goes into root of C bar phi. And then of course, this will reabsorb the fields and rescale all the other parameters, right? And the net result will be an overall constant Jacobian in front of the partition function, but the partition function is invariant, the physics is invariant by any multiplicative constant of the partition function, right? So I can forget about using that term there. So this is as general as the Landau Hamiltonian. This is called the Landau Hamiltonian. Or Landau-Ginzburg model. Now, we will use this model as a prototype of field theory because it happens to describe so many physical systems, regardless of their original physical basis, that is a very standard field to work. And you must have seen this in quantum field theory too, if you were doing 5⁴ quantum field theory as well, which is a standard quantum field theory for bosons, spinless bosons. Okay? So there we go. 5⁴ theory opens, comes back again on us. So we will focus on a theory like this. So we will occasionally change the couplings here. I just want to make one observation. If this is just a side note for the physicists in the audience. In relativistic quantum mechanics, this term and this term corresponds to free particles, right? While in statistical mechanics, they describe paramagnetic or nearest neighbor coupling. Interactions, so not free. What do I mean by this? Well, just to give you an idea, let's suppose we have a field in one dimension for simplicity, okay? And I have it defined on a grid. Then, of course, I have a paramagnetic interaction in the form phi I plus 1, right? But I can define also the second derivative of my field in this one dimension would be like at I to be phi I negative phi I plus 1 negative phi I minus 1 divided a square, right? This is the discretized version of the second derivative, right? Do you recognize it? Now, if I build something like phi I will generate terms in the form phi I plus 1, phi I negative 1, and phi I. Okay? So you see, terms like this actually physically corresponds to nearest neighbor couplings, not with free spins. And if you assume that your system is longer correlation length, that means that you probably need a higher point definition of the derivative, the one that contains more than just 3 points. And that will introduce, higher powers, which means that this, in other words, you will have this kind of interaction appearing, being coupled to large orders derivatives and so on and so forth. So I'm trying to say that, or I'm trying to say that don't be fooled. In statistical field theory, there is no free field at all. Quadratic interaction corresponds to very local interactions. Quadratic Hamiltonians always corresponds to local interactions. Although the same two terms in quantum mechanics correspond to a free particle. Okay? Okay, so let's go back to our Landau Hamiltonian. And we want to do something sometimes the Landau Hamiltonian is also written with the introduction of a linear term in the field. So sometimes it is convenient to explicitly include the effect of a magnetic field. Oh, sorry. In this case, the Hamiltonian will be a functional of the field, but will depend will depend also parametrically on the magnetic field. Okay. Now follow me. This is the physics that brought to us to this Hamiltonian, the paramagnetic analogy. Now let's forget completely about paramagnetism, critical phenomena for phase transition, and let's just consider a statistical theory with a Hamiltonian that is a polynomial function of the fields or its derivatives. For instance, this one. And for reason that will become clear in just a second, then of course there won't be any more magnetic field if these are not spilled. Why having to bother with magnetic field if we don't know what these fields correspond to? Maybe they correspond to density in some whatever situation, right? But let me anyway consider this Hamiltonian with the inclusion of a linear term, which now we call J for the most general case. And I will call this the source term. The J is a source, will be called the source. Okay? And why should we do this? And also in the most general case, let me assume that the source is positive here, because I can always define the magnetic field to be negative the source if I want to have it the right dimension. Now I'm going to tell you why we might be interested in using sources. So in the next couple of weeks, or probably perhaps more, we will be dealing very intensively with this Hamiltonian and this theory. And figure a way out of using this theory to compute objects of interest of statistical mechanics. And what are the objects of interest of statistical mechanics? Well, typically, there are two main classes of objects of interest in statistical mechanics: thermal averages and state functions. Do you agree? For instance, the expectation of value of the field in a point, or the correlation function of the field these are examples of thermal averages or observables that come from thermal averages. And I don't know, if I have my field defined in terms of a j, and I can define this to be e to the negative of g of j, and this is my path integral. This is the Helmholtz free energy, which is a state function. Okay? So these are the objects of interest. And it turns out that basically, if you can compute this guy here, as we shall see later on, you basically can also compute this guy here. If you can compute arbitrarily Green's correlation functions in your field theory, you basically have solved the field theory. So let me state what I just said. If I can compute this guy here, any of them, if I can compute all of these objects, then I can compute not only arbitrarily thermal averages, but in principle, I can compute also, at least formally, arbitrary state function, as we shall see. Whether you can do it practically, it's another different manner. It's another entirely different, question. But in principle, if you have a way to compute arbitrary endpoint correlation functions, then basically you have solved the thermodynamics of your system, the statistical mechanics of the system. And the reason for the first half of this statement is clear. Suppose I'm interested in some observable, which is a function of the field. It can be a local or non-local function of the field. Well, it turns out that since the field is very small, I can always Taylor expand it and basically obtain a series of terms that are correlation functions, right? By Taylor expansion for in small phi. And of course, if I Taylor expand to arbitrarily, if O is an analytic function, I can approximate it to arbitrary accuracy by including sufficiently terms, therefore by including sufficiently many fields in my sufficiently many high order endpoint correlation function in my theory. Just to give an example, suppose my fields represent the density of charges. And suppose my system is a Coulombic system. And my observable is in internal energy. Well, the internal energy would be something like, I don't know, integral dx, integral dy, the density in x, the density of charge in y. I should use rho for density, but I've been using phi so far, so I don't want to change notation. And then, of course, the Coulomb interaction between x and y. This is an example of non-local field. And if I'm interested in the expectation value, basically all I need to know is this guy, and everything else follows, right? Right? So if you can compute correlation functions of any order, you can compute any thermal average of interest. provided that you can analytically express the observables as an analytic function of your fields, which is a working hypothesis we're having. Whether can you compute also state functions is something that I will postpone later, because it will turn out that you can, write state function as sum of infinitely many correlation functions corresponding to what is called loop diagrams in quantum field theory. But I will not discuss this later. Believe me, you have to believe me for now, and maybe you will understand that better later. Okay? So this discussion says that, do you want to solve field theory? Well, the problem of field theory is basically the problem of computing endpoint correlation functions. But the problem, you see, looks formidable, because how many endpoints correlation functions there are in the world? How many endpoint correlation functions can we invent? Of course, infinite, right? You give me an endpoint correlation function, I give you one that contains one more field, right? So one may say, why are you stating this? Because there is a very compact way and useful way to represent field theory, which basically condenses all the information contained in all endpoints correlation function into one quantity that you need to compute. In other words, there is one functional that if you can compute it, then you immediately have all endpoints correlation functions you want. And this is called the generating functional. So what is the generating functional? Is the path integral for an arbitrary value of the source. So I will define H naught as the Hamiltonian without the source term. So going back here, this, for instance, would be H naught. And I will explicitly introduce this on top of H naught. Okay? So also let me use this notation. Okay? This big dot is basically the product between the fields integrated over space. Now, it turns out that if you can compute the generating functional for an arbitrary source, then you can compute all correlation functions. So suppose for a moment, you know this somehow. You have been able to solve this integral, okay? Then what happens if you take the functional derivative with respect to the field, with respect to the source at some point x of z of j? Well, since j appears at exponent, this will be negative integral d phi e to the minus h naught phi minus j phi times phi at x, right? Because this phi at x is actually the functional differentiation with respect to j of x of the integral in dy phi of y j of y. And now if you discretize this, then you immediately understand that this is the integral of a sum and becomes a Kronecker delta. Therefore, we already had this discussion that dj of x y divided by dj of x is a Dirac delta function, right? We had it at the beginning of the course, and therefore this is clear. So now, obviously, if you take this guy, take the negative side on the other side, and divide by j by z, I get something that looks like a thermal average in a theory with j. Now, suppose that j has no particular physical interest in my system. This is not a magnetic field in general. Maybe it's something that I'm not interested in including. I'm interested in the theory H naught. Well, I can take the limit for j going to 0 of this combination. And this would be my first expectation value. In the theory with H naught. Okay, we got one out of the millions that there are, okay, out of the generating function. Let's take another one, and then you understand the rule, okay? Suppose now we are interested in another correlation function, say phi x, phi y. Now the idea is the same. You take the second derivative of your partition function, differentiated it with respect to the sources at x and at y, take away z of j, and then take the limit j goes to 0. So when you take the second derivative, you will get phi at x, phi at y times the Boltzmann's weight. When I divide by the partition function, I will get my term here. And when I take the limit, I will neglect all the terms that contain the sources. So my result will be d phi, phi of x, phi of y, e to the negative h naught of phi. So once you have your generating function R, z of j, okay? If you have your generating function R, z of j, then you can compute any two-point correlation functions. So the quest of solving field theory is basically the quest for computing the generating function R. Now, you might very well wonder whether this has any interest whatsoever. Or stated differently, you might very well wonder whether it's a formal result. You know, after all, if you can compute the propagator in quantum mechanics, then you have solved the quantum dynamics, because you know the wave function at any time, given the wave function at the initial time, due to the propagator. But the problem is that computing the propagator is basically solving an infinite dimension of path integral, and it's infinitely hard as solving quantum mechanics. So the fact that if you know this, you have solved quantum mechanics doesn't really help you in quantum mechanics unless you're very, very lucky, right? Because you need to solve that bloody integral. Now, it turns out that essentially all of quantum mechanics and all of quantum field theory and all of statistical field theory exist because of the following incredible property. Zg, the generating functional, can be analytically computed for quadratic Hamiltonians. Hamiltonians, they are bilinear in the fields. And local. We are going to discuss this in a moment. But before we do that, next lecture, we will explicitly evaluate the generating functional for a quadratic theory. And which is in statistical field theory, by the way, is a highly non-trivial theory, is a paramagnetic theory, right? So it contains physics in it. But I want to spend the rest of this lecture by discussing some implication of what I just said. So quadratic Hamiltonians are particularly common in physics. For instance, who tells me a quadratic Hamiltonian in the relevant degrees of freedom?
The harmonic oscillator.
The harmonic oscillator. Or, in the case that we have discussed, the paramagnetic system, or the Klein-Gordon particle, if you know some quantum field theory. Okay? Now, the fact that we can solve quadratic Hamiltonian has been crucial to demonstrate, to make contact with experiment, at least in some simple cases. The fact that we can solve the harmonic oscillator exactly help us understand Newton's equations and verify them experimentally, because you can study the spring system to death, right? Therefore, the fact that you can study to death brings you confidence on the theory you have. Not only that, we can study statistical mechanics exactly for a particle, a harmonic oscillator, a one-dimensional particle, or a collection of harmonic oscillator, giving us confidence and ability to prove and validate the theory of statistical mechanics. So without being able to solve harmonic oscillator, we basically would have had extremely little room for testing the theories. And therefore, we would have no physical theory, because there's no physical theory if you don't test the physical theory. So the fact that somehow quadratic systems, which are called linear systems, because they're called linear because if you take the derivative, which gives the force, you get the linear force, right? So quadratic Hamiltonians are called linear systems. You have to pull down one. The fact that you can easily solve linear systems, it's basically the reason the theoretical physics exists. And I don't think I'm over exaggerating if I say that in theoretical physics, 90%, even more, 95% of whatever is being done is the result of two things. The fact that we can solve quadratic linear systems, which basically, as we shall see, corresponds to the fact that we can solve Gauss integral. and two, the fact that we know how to Taylor expand. Take away these two main ingredients from theoretical physics, and the entire building crashes to the ground zero. Most of what we do is a small perturbation around these concepts. For instance, when you do scattering and you solve scattering of an electron of a positron, what you're building is a small perturbation on the free electron positron propagation, right? Which is a quadratic theory because particles that are free are quadratic. And so you are Taylor expanding whatever is not quadratic, as we says. Whenever you do, so the fact that we will be able to solve the generating functional for a quadratic Hamiltonian is another surprise, because in theory, quadratic Hamiltonians are ubiquitous and play a fundamental role. So I am not sure I can do it in 15 minutes. Let me see. Well, maybe I can. After all, it's a question that I ask the students at their exams. So probably I can do that. So now we're going to go very general. And so we're going to consider a theory which very generally is defined in the following way. Now, this W is a local Hermitian operator. Okay, examples: constant, Hermitian differentiable operator, potential. Anything like this is an example of local Hermitian operator. Okay? Okay, so that's, we should call this J naught, Z naught, and this is going to be our paradigmatic problem. Compute Z naught. And now, even if I cannot do it today all the way through, let me just give you the idea. Why can we? Let's build the simplest field theory possible. The simplest field theory possible is one in which we have only one lattice side, right? So it's only the field in the single lattice side. Okay? In which case, ZG would trivially be the integral over my field in my lattice side alone in the universe, e to the negative d3a. There's no more any sum here, it's only phi. And since there's only one lattice side, you cannot even define derivatives because that requires at least two lattice sides. So basically, all you have is something like this. And J will provide another linear term. Now, you begin to see why quadratic theories in this simple example are so special, because they almost look like a Gaussian integral, right? You can actually complete the square and make it a Gaussian integral. right? So basically, by complete the square, and I leave it to you for seeing this, you can put the ZG into the form of some prefactor, which we don't care, and something that will be in the form phi minus phi naught square, which will depend somehow on some j. Just play around and make this quadratic, right? For instance, you add the, you get what I do. You get what you need to do, right? We'll do it next time if we cannot. And then, of course, this term will depend on j, and this will be a number that you don't care what it is, right? Because the partition function. So the prefactor will depend on j and will contain j, and everything else, it's a number that you forget. So at least in 1D, it is clear that you can actually solve this theory in the simplest possible case, simply because it is basically the amount of solving a Gaussian path integral out, and all you have to do is to shift the origin so that you make it look exactly like a Gaussian path integral. The shifting will produce a preterm, and this will produce a number which you don't need. Okay? Now, when you will increase the dimensionality, the problem will basically correspond to the same problem in multi-dimension, with your variables coupled through some bilinear form here rather than just a constant. So in multi-dimension, still assuming discretization, this will be like phi 1. Now I'm ordering all the lattice points progressively just for the sake of argument, and I put n lattice points together, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what I have here is like sum over I, j, phi I, wij, phi j, e negative sum over I, ji, phi I. So my path integral, which we know actually is a collection of infinite path integral, infinite normal integrals, is basically a large dimensional Gaussian integral over some non-diagonal bilinear form. Okay? In general. Because this guy here is in general non-diagonal. So the hope will be that I can use the same trick, that is shifting variables, to solve this theory as well. And next lecture, we're going to do that on Thursday. And the result will be what many of you already know, under the name of Wick theorem. But we shall see that. Okay? So I will stop here and do it with all the time it takes next week, next day, next lecture. Okay? Va bene. Buona serata.
Altrettanto, grazie.
Grazie, arrivederci.